Okay. First of all, thank you for inviting me today to give this talk. It's true, I come from Italy, and when I moved to this great country that is Australia, I tried to bring my expertise, that is more in hard rocks and big mountains in the North Alps of Italy, to Australia. When they asked me to come here today, they asked me to speak about innovation, about research, and about mining. So I started to think about what is really, for me, innovation. For me, is first of all having a vision of something that can be done, something that can be improved. But for doing this, you need the investment. And the Australian mining industry invests every year over $3.8 billion Australian dollars for research and development. This is important because if we think about the research that is conducted in the Australian environments that are, let's say, difficult environment within remote areas of the country, we can gain an experience that is fundamental and can be exported all around the world. So the Australian mining industry invests because acknowledge the significance of the research and development. That for me is taking researchers, putting them together, work in a team, and develop new cutting-edge technologies. And this cannot go without the training and the education that allowed us to bring our expertise, first of all within the Australian people, and then to disseminate this expertise in the world. I would like to show, this is going very fast, to show you this sentence that says that the Australian companies lead the world in mining technology, services and equipment because they spend so much of their time and effort in the area of innovation. But innovation is not only technology, it's not only manufacturing, and the mining services such as the workplace safety continue to play a key role in the expertise and global reputation of the Australian mining sector. So the mining equipment, technology and services is making Australia the top level. And the main reasons for that are the increased government safety and health regulations, and increasing of the global mining company safety codes, a new demand, continuous demand for innovative research within the mining environment. It should be mentioned that the Newcastle University, together with the Newcastle Institute for Energy and Resources, opened a new Centre for Resources, Health and Safety. The principal objective of this centre is to identify and to solve the needs that bring a healthy, safe and well-being in the mining sector. This is carried out by promoting the collaboration between industry and government agency and using the multidisciplinary experience of the researchers of the University of Newcastle. And my talk will be really about safety. So first I will give a short overview of the problem that we are assessing that is related to rockfall. And then I will show you new techniques that have been developed by the researchers of the University of Newcastle to improve and to investigate new strategies to ameliorate the rockfall hazard within the open-cut mines in Australia. At the end of my presentation, I will also show you some of the latest research on energy absorption capacity of muck pile for mining applications. Rockfall barriers are used through Australia to protect the extensive road and rail network. This network is fundamental for the growth of the country and for maintenance of the economic growth. But thousands of cuttings along the roads are characterized by possible potential rockfalls. Rockfall is a phenomenon that can take lives, can make very big damages for infrastructure, machineries, and also in the mining environment is a really significant hazard. If you look at this high wall, you can understand that a block that is detaching from the top of the high wall can pose a significant risk for mining, for the personnel working at the bottom. For example, if we have a heavily worked area, damage to the machineries, or also a loss if the mining activity needs to be stopped for safety issues. So if you see these images, there are some of the pictures that I took during my research, both in New South Wales and in Queensland Mine Science. These are portals for underground entries and blocks around the portals. Rockfall hazard doesn't mean that we always think about big block coming from the big mountains and is coming on top of you. But small blocks can kill. They can go extremely fast, and they come without any warning anyway. So this induces us to really think about the necessity to manage the rockfall hazard at the base of the high walls. What do we do, and what is common practice within the Australian open-cut mines, is to use some draperies. Draperies are active protection measures against rockfall that are put directly on top of the high wall, like you can see here in this image, and they actively protect from the possible blocks that can detach from the high wall, but in the meantime control the motion of the block that is detaching and falling between the rock surface and the net, and then reduce the impact energy that the blocks can assume when they impact at the bottom. However, blocks can still detach, can still fall between the drapery and the rock surface, and can impact at the bottom with quite high energies. I don't know why he's going straight away by himself, but okay.
Active measure can be used depending on the location, the geometry, and on the conditions. We can see simple mesh fencing or more secured fencing where more than the mesh, the wire still meshed.
Okay, I start again. It was not me, but okay. I was talking about draperies. For what is not in people that are not in the field, we can use different typology of drapery mesh depending on the conditions, on the materials, on the problem that we're trying to solve. We can have simple mesh that are just anchored at the top of the high wall, or more advanced mesh that we call also cortical strengthening, that combine to the mesh, to the steel wire mesh, also a raster of nails that try to fix the superficial blocks. Okay, but we don't know how efficient are these draperies. I saw reports, I saw studies, I saw calculations of people that assume that because just we have this drapery, the energy that is coming on top of the portal is almost nil. Values that, if you really study, they assume that the safety is completely covered by just the presence of this drapery. But there is still a residual hazard. Can I do by myself?
An aspect of the problem that we have to consider.
There is still a residual hazard that needs to be assessed. And the mining industry requested us to investigate and to study this.
Of these portals.
Generally, when we talk about rockfall, we refer to three main steps. One, the initiation of the problem. So it means to understand where the block is coming from. Then we investigated the trajectory, so the transit zone. And finally, the impact or deposit zone. In the initiation zone, we needed to understand why, when, and what is coming down. So it's very difficult because rockfall is usually a phenomenon that happens without any warning. For the trajectory, we need to understand where the block is going and which is the block energy that during this fall and impacting along the slope, the energy is going to be loser. Then the impact zone or the deposit zone is important because allow us to design the protective measures. Once we know where the block is going and how much is the energy that we have to protect for, we have the information that allow us to design an appropriate mitigation measure. When and what can be assessed through the expertise of geomechanical survey, and then the trajectory is usually analyzed through back analysis. Sorry, the presentation is going by itself. I don't know why. So usually we do rockfall test and predictive models. I'm trying to speak fast to follow this.
I don't know what's going on.
Okay. Very shortly, if the presentation gives me the time, what we want to do is to use two main steps. The first one is to identify the blocks, so the shape and the size of the blocks. And then in the second step, what we want to do is to do a modeling that allows us to predict what can happen. We were very lucky because with the support of the mining industry, we had access to the Minesite, where for the first time we were able to carry out full-scale testing of rockfall under the drapery net. So the Minesite was Beltana mine in the Hunter Valley, close to Singleton. And indicated here with the red arrow, you can see the 1.4 kilometers of high wall that has been studied during this research. In particular, this high wall has an area that we used for the test. And this area is around 85 meters long and 40 meters high, 70 degrees deep. So we selected two specific sites where we carried out full-scale rockfall test. The first site is behind the net, and the second is on free fall without the net, in order to be able to compare the results. As you can see in the image, we positioned a 60-ton terrain crane on top of the high wall, and we dropped the blocks. We dropped the blocks from the top of the high wall under the net. Okay, with a man basket. This is an example of the block, the fall of the block. And then, using high-speed video camera positioned on top, in front of the high wall on the road, we use a 3D stereophotogrammetry to measure the trajectory and the velocity of the blocks. And we obtain this. It will be great to be able to carry this type of test all the time, but I can't tell you the amount of time and effort, first to convince the Minesite to allow me to do this. Second, all the safety procedure that we have to go through in order to have access to this site. Of course, this specific site, we were able to use that because the underground activities were already completed and there were no safety issues for the personnel working around these portals. An alternative, when it's not possible to conduct physical testing, we use, because physical testing involves, is very expensive, because what I show you costs a lot of money, time-consuming. Alternatively, what we can do is the application of numerical models. So, first step of our approach, the second step of our approach, was to create the model. What we did is to use some randomly pictures that can be taken with any type of camera, even the small camera that you're using for your tourist trip. And we collected these pictures and we built a 3D motion reconstruction of the high wall. This is a point cloud coming directly from the images. These data were then imported in a code, in a software, in a distinct element model. You can see the level of details of this reconstruction. And in the model, we were able to reproduce the surface to give the property to the materials, where we have sandstone instead of mudstone or coal, and to run the analysis once we build the mesh. And we drop the blocks like in the same way that we did in the experimental site to calibrate and validate the model. So here you can see the blocks, and soon in the right side of the video you will see the second impact on the block, and finally the impact of the block on the muck pile, on the waste material at the bottom of the high wall. Comparing the experimental to the numerical results, we had a very good agreement. And then we could apply this methodology to other high walls, to other geometries of blocks that can potentially detach. So we could investigate the efficiency of the drapery. We could work optimizing the mesh. For example, if we need some ropes or anchors at the base of the high wall. This is the application of the methodology to another high wall, completely different side, different block, but we have anchors at the bottom. We can investigate if the mesh has failures with particular geometries or particular energies, or if we have several blocks that are falling. Usually we consider this like a lot of small blocks that are coming from the top level of the high wall. So a lot of information came from this research, and the ROCCO recommendations that it was what the industry was looking for. Also related to the muck pile, that is this amount of waste granular material that they use to put on top of the portal, and they assume that it's enough to protect their concrete structures. The outcome and the results of this research make us and the industry think that there is really a need for a rigorous methodology for rockfall hazard assessment that should be specifically adapted to the coal mining. So the next step, and what is currently ongoing, is the research in order to develop a new methodology that involves two levels of rockfall assessment. One is a qualitative first. So the surveyor, the geologist of the mine site, can go on site, bring his iPad, and do a qualitative first, quick assessment. This is an area we have to be careful. Why? Because the structures are in this way, because there are potential blocks that I can see. I can say, step in front of the high wall and understand that there is a problem. The second step is a more rigorous or more strict assessment that involves the use of a matrix. So depending on the life of the mine, we will consider the different level of hazard directly from the information that we gather on site. And we say, okay, for this area that was potentially at level, at a high risk, we can say where is the hazard, high level, medium level, or low level. And the consequent protective measure can be used. But there is not only rockfall, and the industry, looking at this result, especially the result related to the muck pile, came again to us, and together we thought that it was necessary to study other aspects, other geotechnical aspects that can bring the safety in the open-cut mine at risk. For example, the muck piles are used as energy absorption barriers in many surface mining applications, like berms at the dumping point, windrows at the crest of the high walls, or traffic separators. These barriers, these safety berms, are usually built using a rule of thumb. And the rule of thumb is that the height of the berm should be at least the half of the diameter of the biggest truck on site. But with the new generation of haul trucks, is this rule of thumb still valuable? If we look at some statistics, the 53% of the accidents that involves berms are related to accident related to berms. And the 70% of them are related to dump, to trucks going through the berms in the dump site. So these are some images to show the hazard that I'm talking about. We have to consider that these guys, the drivers, work in conditions that can be during the night shift. Sometimes they are under heavily fatigue because they are working a lot of hours. So why cannot we improve the conditions and the safety? So should we do something that improve the design, the construction? Should we provide guidelines that help the mining industry to improve the design of these berms? Again, I was lucky enough, or probably I stressed a lot to the mining industry, but I convinced them to give me the space and the funding to make me doing some experimental testing. I am an old-fashioned engineer, perhaps, and I like to see the things that I'm then modeling. And with the collaboration of Glencore and Anglo-Coal, we conducted several tests, in total 28 tests, where they built a berm for us, they give us the space, and we used 3 types of new generation haul trucks, the 797, 793, and 789, where we were able to compare and to test different types of shape and geometry of berms. Again, we used the high-speed video cameras and on both sides of the truck, and we measured the wheel climb, the wheel displacement, and all the motion during the impact. This is an example of the test with the 797 in one of the first berms. Okay. And these are the data that we were able to collect. So we measured the approach velocity, the maximal wheel climb, and sorry, it's going by himself, but that's okay. The second series, this is a nice test. This is a multiple impact test. I have to tell you that I lost almost 10 years of my life at the third impact, just thinking about the amount of money that I should have paid if the truck would have been damaged. And you see, and then there is the third one. Should come now. Yeah. That was the last one and the hardest one. I was sweating at this point. I didn't want to watch. But yeah, and these information, these tests were extremely useful for us because they allowed us to calibrate the model later on. And first, with a very advanced 3D photogrammetry reconstruction, we rebuilt the berm. And with the photos of the berm before and after, we were able to measure the tire sinkage and what was the effect of the truck on the berm. I was not happy enough because for safety issues, I couldn't do the test with the forward motions. I mean, there was no way to convince the Minesite to allow me to do that. So I said, okay, let's have a little bit of play, and my students were happy, very happy to help me with that. And we rebuilt the conditions in the lab at the civil engineer department. He's going on by himself, I don't know why, but okay, let's see. Okay. In this case, it's the forward motion recorded in the lab. And in this case, I could increase the velocity. I could go even over 20 kilometers per hour in full-scale terms, and observe the punch-through of the truck or the rollover of the truck. This is an example of the main accident that you can observe and the risks. And with all this data now, I was able to calibrate my model and to validate that. Okay. So you can see this is a simplification, but I can observe the punch through the burn. At this step, I have everything. I have the data from the full scale. I have the model that is correctly calibrated, and I can change the geometry. I can change the particle size distribution of the waste material, and I could produce some guidelines for the mining sites that can allow them to improve their design. So finally, to conclude, I think that what I presented is really how research and collaboration between the mining industry and the researcher can produce something that is really applicable, not only to the Australian context where the things has been developed, but all around the world, because these methodologies are now already used in other sides of Australia, but also could be applied in very difficult conditions, mine sites in other countries, and improving the safety for the workers and for in all the areas that are potentially affected by these hazards. I would like to thank you for all this work. First of all, the Australian Coal Association Research Programme that believed in me, and they were extremely collaborative, supporting me, providing me the sites and the funding to carry out this research. And also my amazing team of students, technicians, and researchers that have been the passion and the expertise to spend hours and hours with me in the mine site and hours in the lab, and again analyzing the amount of data that we collected. They were really, really great. Of course, for the main mine companies are Glencore and Anglo Coal that helped. At the moment, there is also Rio Tinto that is strongly involved in research and supporting us. Finally, I liked this, and I think it's a good point to everybody. And sometimes my son asked me, he said, people ask me what job my mom does. And he answered, my mom plays with rocks. And I think he's right. I like playing with rocks, but for good solutions. Thank you.